we'll continue. And let me remind you where we are, what the big picture is. The big picture is, there are sometimes, when someone says, is this convex or this concave? Sometimes you actually just go back to the definition or calculate a Hessian or something like that. That's actually really very rare. Really, the way you're going to be doing this, and a lot of people do this in practice, is in a constructive way. And so that's basically a calculus, as I said. You learn, a bunch of base convex functions, a bunch of base convex sets, and then you learn the rules that you can use to combine them and to know that the combination, or to transform them, and to know that that transformation is also convex. And so then, in fact, that's going to be also how all the code works as well, as we'll see. So, okay. So we're going through these. I think last time I mentioned these. Some of these are simple and obvious. Pretty soon, though, they're not simple or obvious, right? Some of these rules. So the first are, look, if something is convex, then 3.7 times it is convex. Well, sure, right? If something curves upward, and then you multiply it by 3.7, it curves more upward, right? So that's fine. The sum of two convex functions is convex. And again, some of these things, and I would actually encourage you to do this every now and then, you just grab one of these things and just prove it. Some of these are like 3-line things to show, but somebody has to show them. I'm not going to do it, right? So, the sum. Precomposition with an affine function. Precomposition refers to the fact that the affine function appears first, right? So first I apply an affine function, that's ax, I map x to ax plus b, and then I take this convex function f. And that preserves convexity. And again, this is not, these are not, that's a 3-liner, and so it's, these are the kind of things you might want to just show yourself. Okay, so these are relatively simple. Then we get to the so-called pointwise maximum. So the maximum of a bunch of functions is defined pointwise. And, just to convince you that this would preserve convexity, I'll just draw a picture. It's not too hard to actually show it. But if I have, one function here, and I have another one over here that's convex, here's another one, right? Then if I look at the maximum, the pointwise maximum is going to be this function here, like that, okay? So that's what and it's pretty clear, at least your eye tells you that's convex, and it's not hard to show this. So the maximum of a bunch of convex functions is convex. That's sort of a basic thing. It's kind of obvious. So here's a so-called piecewise linear function, right? One way to describe a piecewise linear function, by the way, the canonical way is to say, oh, well, here is to actually have a Voronoi decomposition of Rn, and then in each one to specify the affine function. In each region, you specify the affine function. That's sort of the typical way. Actually, for convex piecewise linear functions, there's actually a lot. There are many other ways that are sort of better to represent it. One is simply the max of a set of affine functions, right? So there, I give you a bunch of affine functions, and then I simply take the maximum, and that function is going to be convex. That's a convex function. Here's a very interesting one, is the sum. So here's a function on Rn. The sum of, let's say, the 4 biggest entries. Everybody got that? So it's a weird function. It is, in fact, you can kind of, it's quite complex. It's not differentiable. The derivative doesn't exist at some points, actually. Let's see, it certainly doesn't have a Hessian, right? It turns out this function is convex, right? And the way to show that is actually pretty straightforward. What it is it's the maximum of a bunch of functions. This function here, it's all possible sets. Let's do some of the 4 largest entries. It is all possible subsets, choices of 4 entries in the vector. And I sum those up, and then I take the maximum. Now, how many are there? N choose 4. If n is big, that's actually a very big number. Doesn't matter, right? So this is convex. Everybody, this makes sense? So this is the sum of so people refer to this as the sum of the R largest, or the sum of the K largest. And it's a convex function. That's not totally obvious, I think, right? By the way, you can extend this to the sum of the 5.6 largest entries of a vector. What would that mean? What's the sum of the largest 5.6 entries of a vector?
Weighted average.
Well, weighted average? Yeah, kind of, but like, let's be more specific. I give you a vector, and I say, what's the sum of the 5.6 largest entries? You tell me what to do.
Is it just the sum of the 5 largest entries?
It's the sum of the 5 largest entries plus 0.6 times the 6th largest. Everybody got that? So yeah, when you said take a weighted combination, sure, but that was vague and I wanted something more specific. So, everybody got that? That's a weird function. Guess what? It's convex, right? And you can, it's the same thing, right? That you simply look at all possible combinations of sums of, actually you could do in this case 6 things, with one of them having a weight of 0.6 and the others having a weight of 1, right? And you just sum over all of those. There's a lot of them, doesn't matter. Each one of those is linear, and the maximum of a bunch of linear functions is going to be convex, okay? So, okay. Now this actually generalizes to a supremum, right? So supremum is, if you've had analysis, you know what it is. If you haven't, it's basically the maximum of an infinite number of numbers, right? I mean, and there's some subtleties, right? Like it could be infinity, for example, which is not possible if I have a maximum of a finite number of numbers, right? So that's what so if you see sup, you can just replace this with max and you will be just fine. Okay, so suppose I have a function of 2 variables, x and y. By the way, here, x is a vector. Turns out y doesn't even have to be a vector. It could be some weird thing. It could actually be some combinatorial structure, like a path and a graph, or something like that. Doesn't make any difference. It's anything at all. And so you might even think of this as a family of convex functions parameterized by y. That would be a good way to think of this. And it says that if you simply take the maximum over all of these values of y here, that gives you a function, and it's convex. And this is also not too hard to show. Okay? Okay, so we can look at some examples here. Here's one. Let's see. Oh, this is the support function of a set. So if I have a set here, then the maximum over the set of y transpose x, that is a function of x, that is actually convex. Okay? By the way, there are no restrictions whatsoever on the set C. Doesn't have to be convex or anything. Yeah?
When it says y is an element of A, what is that A?
Script A is actually any set at all. Anything at all. That was my point before when I said it doesn't have to be a vector. Sometimes it is a vector, but it doesn't have to be. It could be some weird combinatorial structure. It could be literally, it's the maximum over all paths in a graph that would take you from here to here. It doesn't matter. It's anything, so it could be anything at all. Permutations, stuff like that. Okay. Here's one, let's take a set C, not necessarily convex. And we work out here the farthest distance to the set, right? So what is the distance to the farthest point in that set? That's the usual distance is the smallest so if someone the universal definition of the distance of a point to a set. So let's see. Here's a set, right? The universal definition of distance, if this is x and this is s, so distance of xs, it's the minimum distance. So it would be something like that. Okay? This is the farthest distance, right? And so that would be, I have no idea what it would be. Maybe it's, who knows? It's either this point or that point. It's something like either that, something like that, or maybe something way over here. I'm not sure. Anyway, that farthest distance is convex, right? And by the way, it's not too hard for you to start imagining applications where things like this would come up, right? So this could be a set where you want to provide wireless coverage. X is a is a base station or something like that that you're placing. And then this becomes very interesting because it's the farthest distance from your base station to a place that you're, contractually required to cover or something like that. So we're starting to get close to things that are clearly useful in practice. Right? So we'll get to that. Okay, here's a good one. The maximum eigenvalue of a symmetric matrix, right? So now the maximum eigenvalue of a matrix, that's a really complicated function, right? It's basically you form the determinant of lambda I minus a. That's an nth degree polynomial. You find the roots of the polynomial. In this case, they're all real. And then you take the largest of those roots. And you might know that if like the polynomial has degree 5 or larger, there's no like formula for the roots of a polynomial like there is for quadratic that you know. Some of you might have seen it for a cubic. Anybody? I'm hoping they don't teach that anymore. I'm super happy to hear that no one knows that. And for a quartic. Part of the reason they don't teach it is because the quadratic formula. That's totally fine. Cubic, it's like a paragraph. Quartic is a page and a half. And it's not cool. And then, of course, mathematicians sat around and said, well, what is it for the quintic? And then essentially it was shown, I don't know, 200 years? Is it 200? Yeah, it's coming up on 200 years ago. It was shown, actually just about 200 years ago, I think, it was shown that there's actually no formula for the quintic, so they could stop. Now, of course, that doesn't stop anybody who actually does stuff, because people find eigenvalues and solve and find roots of polynomials like every day, all day long, but they do it numerically, right? But there's no secret formula for it. Okay, all right. That was a long, weird thing. Okay, all I'm saying is the function, which is the largest eigenvalue of, let's say, a 10 by 10 symmetric matrix, it's a really complicated function, right? And I can't write it, there's no formula for it and blah, blah, blah. But it's convex. And the way to show it is really simple. What kind of function is y transpose xy of x? It's linear, right? So this shows you really have to be on your toes, right? If I write that thing out, right? So if I write out, what is it? Y transpose xy, right? That's the sum over I and j of yi, yj times xij. Now this function is quadratic in y, but it is linear in x, okay? So that's actually going to be sort of a theme, is that a lot of times you just really have to be on your toes, reminding yourself what's the variable, what's not, all that kind of stuff. And things that don't look linear actually sometimes are. Or we'll get to examples of that. Okay, so here it is. This thing, y transpose xy is linear and therefore convex for any value of y. It's a linear function of capital X, right? So but now this says if I take the supremum over everything on the unit sphere, so y is this, sphere, then this thing just turns out to be, first of all, that's convex, but it also is the maximum eigenvalue. Okay, so does this make sense? So it's going to get, things are going to slowly get a little bit more complicated and maybe less obvious. Okay, now we're going to do composition. This is actually super important. You'll know why in about 5 minutes, 10 minutes. I'll make a big deal out of it because this is going to be actually a huge part of your life for the next, well, certainly for the next 8 weeks, it will be, and quite likely long after that. Okay, so we'll just start simple. It goes like this. When is the composition of two functions, convex? So when is h of g of x convex, right? And we know one, by the way, we already know one version of this, of composition. If g is affine, then, and h is convex, this thing is because that's precomposition with an affine function. That's convex, okay? We're going to go beyond that now, okay? We're going to have g be not affine. Okay, so here's the rule. It says that this composition is convex if g is convex, h is convex, and I'm going to be very just informal and just say increasing. So an increasing convex function of a convex function is convex. Okay. Now the h tilde means it has to be non-decreasing this extended value extension. So and that's not a weird technical. It's actually a real thing. But the rough way to think of it is increasing function of a convex function is convex. Most famous example, if g is convex, then exp g of x is convex. Okay? So e to the x squared is convex. Period. Right? Why? Because exp is convex and increasing. And what this says is convex increasing of a convex function is convex. Here's one. It also works this way. If h is decreasing, if the outer function is decreasing, if it's convex and decreasing, then if g is concave, this composition is convex. Okay? So that, and by the way, you can get that from the other one by substituting a minus with g and stuff like that, right? So that would do that. So here's an example. 1 over g of x, the inverse of a positive concave function is convex. Okay? So, I mean, you could check some things like, let's say 1 over square root x. Square root x is, let's limit it to, it doesn't matter, is non-negative and so on. So 1 over that is actually convex. Okay? And the reason is the function 1 over x is convex and decreasing, right? So it looks like this. That's 1 over x, right? It's both convex and so actually, please note that all of these arguments involve basically the signs of the zeroth, first, and second derivative. Because I'm talking increasing and decreasing is the sign of the first derivative, if it's differentiable. Right? Convexity and concavity, that's the sign of the second derivative. Again, if it's differentiable, but this is not a bad way to think of it. Okay? And then we also sometimes say, well, something has to be, okay, here, g had to be positive, otherwise 1 over x, at least in this class, doesn't make sense, right? So, okay? Okay, so these are the composition rules. And lots of ways, it's actually very short to just prove it directly. And with no assumptions on differentiability or anything. But I think a very good way to think of it, the way I think of it, or my mnemonic for it, if I forget this, I guess I don't forget it. But if I were to forget it, I would simply go back to something like this. You just assume everything is in Rn, R1, sorry, it's in R1. Assume everything's differentiable. And then you literally just take, go back to your calculus class, differentiate this once, you get h prime of g of x times g prime of x. Differentiate it a second time, and you get this thing here. And now we look at that formula, and you take a look at it. And let's do the second one. How about this one? Okay. So, and by the way, these assumptions are going to tell us about the signs of derivatives of order 0, 1, or 2. So let's see how this works. So let's look at this one. G is concave. Well, let's see what that means. That means that's a negative number. Right? I'm going to be a little, informal, right? I'm not going to distinguish between positive and non-negative and all that stuff. So this is negative, okay? Let's look at this. So let's see, h prime of g of x. Well, let's see what, h is decreasing, right? So that means h prime of g of x, that's also like less than or equal to 0. And now we're going to use a very deep mathematical fact. You ready? The product of two numbers, each of which is less than or equal to 0, is bigger than or equal to 0. Everybody got that? Extremely deep mathematical principle, right? So literally we're using the dumbest sign arithmetic, for multiplication. So this term, with these assumptions here, this term, bigger than or equal to 0. Now let's look at this term. Well, g prime of x squared, well, any square of anything is going to be non-negative, right? And then then we multiply that by h prime prime of g of x. But we're assuming h is convex. That means that h prime prime is non-negative. Everybody got it? So once again, deep mathematical principle, the product of a non-negative number times a square of another number, that's going to be non-negative. And now we're going to use an even more basic fact, which is the sum of two non-negative things is non-negative. Everybody got that? So all of this is non-negative. Oh, but that's f prime prime. That's exactly what it means for f to be convex. Okay, did everybody follow that? I mean, it's kind of a dumb thing, but I wanted to go through it. It doesn't hurt to go through it. Yes?
Is this just in one direction, or does it hold the other way as well? Or like other examples?
It does not hold the other way. So that's a very good question, right? If this composition rule, if the hypothesis of the composition rule holds, you can conclude something is convex. Right? I mean, there's a similar one for concave, right? You can have cases where the composition rule does not hold, and yet the function is convex. Okay, so that's an example, right? We'll see many examples of that, right? So, okay, everybody got this? Okay, and here's the main one. And actually, there's only just one variation on this, and then it's the one that will be a very important part of your life. So here it is. It says, now what I'm going to do is I'm going to have h has multiple arguments. So h is a convex function on vector arguments, right? So, and g will have, let's say, k entries. G of x I'm writing for this for the arguments, which these are the entries of g, g1, g2 up to gx, right? And so here's your composition. And let's see what the rule is. This. It says that f is convex provided the outer calling function is convex, and then there's two statements here, although in fact the stronger statements you can mix them, but here it is. It says, here's one case, it says that h is increasing in all the arguments, and these are all convex. Here's another one. H is decreasing in all of the arguments, and these are all concave. Oh, by the way, here's another one to round it out. H, no conditions on monotonicity on H, but all of the arguments are affine. Everybody got that? Okay, so now it's time for me to tell you the full story. It's actually, I think we have a homework problem on it. I mean, it should honestly have been a problem in the book, but too bad. Then it's this. The most general form says this function is convex provided, now I'll say it, you're going to see this. You're going to live and breathe it for that matter, but it's going to go like this. It says provided h is convex, and now I'm going to iterate over the arguments. For each argument, either A, the argument is affine, in which case there's no monotonicity requirement on h at all. B, that argument is convex, and h is increasing in that argument. Or C, the argument is concave, and h is decreasing in that argument. Okay? So it just mixes, you can just freely mix and match these things. Affine, convex, concave, and monotonicity. Everybody got it? So actually, here's what's weird. That one rule subsumes like basically all the others. Like, let's give a really weird, pedantic, long proof that the sum of k convex functions is convex. Okay? Now, first of all, that's obvious, but let's prove it using this. So I'm going to show that this actually subsumes all the rules you've seen so far. So let's do that, right? So here's the way I'm going to do that is I'm going to make up a new function. It's going to be, so h of, let's say, z1 up to zk is going to be this. It's going to be z1. I'm going to add them up. Okay? That's my function. Okay? Somebody tell me about curvature of that function. Is it convex? Is it concave? It's both. Okay. But I'm doing convex, so it's convex. Okay? Now tell me about monotonicity of this function in its arguments. That means if I increase like x1, does that function go up? z1, does that function go up or down? Okay, so it's monotone in all the arguments. It's monotone increasing. Here, by the way, that's actually true. It's not just non-decreasing, it's actually increasing. Everybody got it? Okay, now I'm going to apply this. I mean, this is ridiculous, but I'm going to apply this fancy theorem. And it says, therefore, if I have, g1 of x up to gk of x, and if these are all convex, then we conclude using this thing here that this thing is convex. But that's the sum. Okay? So that's a pedantic, long-winded way to show that the sum of convex functions is convex using the composition rule. Okay? We could do it for max. Let's do that just for fun, just to show you that it's the same thing. Here's my function. Okay? So let's talk about h. Tell me about curvature of h. Convex? The max of a bunch of, yeah, it's convex. Okay? Is it concave? No, not in this case. Well, okay, if k is bigger than 1, It's not concave. It's not affine. It's not concave. Okay. Tell me about monotonicity of that function. It's non-decreasing in each argument. In other words, if I increase any argument of the max, it can't go down, so it's non-increasing. It doesn't have to go up, right? Unless I grab one of the things that's actually active at the max and then I push it up, then the max goes up. Everybody got that? So, okay. So that, again, this thing applies. And so I didn't really need to show you, I guess if you wanted a minimalist thing, I didn't have to tell you about the sum of convex functions and the max and things like that, right? So, but I think humans think of it more like these things and you sneak up to it, right? So, okay, everybody good? So, I mean, here would be, something that's not totally obvious is log sum exp of a bunch of convex functions is convex, right? Or you might say this, the soft max of a bunch of convex functions is convex. These could be losses when you're fitting a statistical model, and this says that the log sum exp is a convex function, okay? Why? Because log sum exp is A, convex, B, increasing in all arguments, and therefore the arguments could be replaced with convex functions. Everybody got this? So this is the composition rule. It's extremely important. And also, this, maybe I'm getting a little bit ahead of myself, but this is actually, you can almost very easily imagine something like this in some object-oriented system, right? Where it would do very cool things like, to check F, you literally walk the expression tree, right? You look at F, actually, all you have to do is ask, tell me your curvature and monotonicity, right? And it would say something like, I'm convex and I am monotone decreasing, okay? Then, you get something for each argument. Then you literally iterate over the arguments and call the same method on each of the children in the expression tree, right? And this gives you like a one in a real language, like one line that would allow you to actually parse and verify whether an entire expression satisfies this, which means that expression is convex. The converse is false, of course, right? That it can fail, the composition rule can fail, and yet an expression can be convex. Okay, so I'm actually getting ahead of myself, but this is already starting to get, it's close to super useful and interesting. Okay, yeah?
Sorry, why is max convex?
Oh yeah, so that's just, you just have to show it, right? That the max function is convex, right? This is circular, but I could say it's the max of a bunch of linear functions, which is x1, x2, but that's weird because that's what we're trying to show here. So you'd actually just have to show that. Yeah. For things that simple, you could actually do something. You could give me an x, give me a y, give me a theta between 0 and 1. And then just, write it down. And actually in that case, in about 2 lines later, you will have what you want. So, okay. Yes?
Is this supposed to be convex? Is there a typo there?
Where?
The example is written summation log g of I is concave.
No, that's correct. Yeah. So let me explain why. Oh, I'm sorry. That's a very good point. I didn't say this. So by flipping the sign here, you get a similar composition theorem for concavity, right? Because something is convex if minus f, something is concave if its negative is convex. Then you apply this rule. But when I negate a function, all sorts of weird stuff happens, like its monotonicity switches, right? If it was increasing before, now it's decreasing, right? And its curvature switches. Yeah, so this one is using an analogous composition rule for concave, right? So let me explain that. A concave function of a concave increasing function of a concave function is concave. A convex increasing function of a convex function is convex. Right. That's for when you have one argument, right? Then we could do the case with multiple arguments, right? If you want, let's actually just do one for fun that's not obvious. Okay? So here's a function. This is x squared over y. And the domain is going to be y positive. Okay, so this is that it's the simplest function that most people on the streets would not know is convex. Okay, so that's convex. So this is convex. Let's talk about monotonicity. Is it monotone in X? That's its first argument. Is it? I don't think so. Unless, right, because X squared, it actually has a negative slope if X is negative. Yeah, by the way, if X is non-negative, then this is monotone increasing in X. Okay? Everybody? Okay. Okay. What is its monotonicity in Y? It's what? Is decreasing. Okay. So what this means is, if I want to satisfy those rules, it says I can replace X with an affine expression. That's the first thing I can do. And for Y, I can replace it with a concave expression. So the following is I could do something like this. Here you go. Maybe I'll use Z for this, right? And then X for my other one. Okay, so this is Y. So I'll have this one. Here's a function. Ready? 1 transpose X squared, right? That's the sum of the entries of X then squared, divided by, I don't know, let's say the minimum of 2 and square root of Y. Okay? Yeah, in fact, you know what? Let me do something even weirder. Let me make this the square root of x3, its third entry. There you go. Okay? There's some sick function on Rn. I mean, you agree that it's a very weird function, right? But it's completely clear what it is. I have no idea where it might come up. This says sum the entries of the vector and square it, and divided by the minimum of 2 and the square root of the third entry of the vector. Everybody got that? Oh, and I'll have in this case, it doesn't matter, but I'll just say this. Okay? Everybody got the function? Now, if I asked you, is that convex or concave? Let me tell you some things you would not want to do. You say, well, here's x and here's y and here's theta between 0 and 1, and then start arguing. You don't want to do that. You don't want to take a Hessian for many, many reasons. Number one, this is not differentiable. Okay? That's number one. Number two, even if it were, you don't want to take a Hessian. Trust me. Everybody cool? Okay. And now we're going to show that this is convex just using this rule over here. So let's walk through that. How does that look? So this is the kind of thing you will be doing this for 8 weeks minimum. Okay? So it goes like this. You're going to say, well, let's see. You look at this function. It's convex. We know that. It is neither monotone nor increasing nor decreasing in Z. But I can put an affine function there. And that would be this. So this is perfectly cool. This function is decreasing in Y. So I can substitute for Y a concave function. Now, is this concave? Let's again use the composition. Let's just go slow with composition rules. Is the constant 2 concave? Yeah, it is. Okay. How about square root of x3? That's concave. And in fact, if you want to get real fancy about it, you'd say, oh, that's the square root function precomposed with a linear operator, a linear function of x, which simply pulls out the third entry. Everybody got that? I mean, that's if you want to be real fancy. Or you can just say, nah, it's concave. It's fine. Everybody got me? Okay. How about the minimum of two concave functions? Well, I should have said this earlier. The max of 2 convex functions is convex. Turns out the min of 2 concave functions is concave. And you can verify that with rules like this one, right? Which you probably know, or something like that. That the min of AB is something like minus the max of minus A and minus B. I hope I got that right, but I think it feels right. If that's not right, something really close to it is right. And that's what I meant. How about that? Okay? So, you can't say that in an undergrad class. I can say that in a grad class for sure. I don't have any problem with that. Okay? Everybody Everybody good on this? Okay, so basically then by the composition rule, this crazy function here is convex, right? And basically, if you didn't know about this, I mean, all I would say is best of luck to you to show to recognize that function is convex or to show it. Everybody got it? So what we're doing here, we refer to this as constructive convex analysis, right? That we look at a function or an expression, and what we do is we try to build it. It's constructive. You literally, you could start at the leaves of the expression tree, right? Like, this thing and that thing. And then actually literally look at the expression tree, walk up the tree and label every node as either convex, concave, maybe affine, right? And then just check if this rule applies at every node in the expression tree. Okay, this is all this. I know you're seeing this only for the first time, but you will see this so many times it's not even funny. Yes?
Sorry, quick question. Why is x squared over y not monotonically increasing in x?
Because what if x is, well, let's take, I'll show you. Let's take y equals 1, and I'm going to take z equals minus 1, and this would evaluate to the number 1. And now take z equals 0. Well, now it evaluates to 0. Because z just went up and the function value went down. There you go. Now, if I go from 0 to 1, it goes up. By the way, it's a very good point. Since we're doing sign arithmetic on the 0th, 1st, and 2nd derivative, suppose I told you ahead of time that z was non-negative, right? If you knew z was non-negative, then you could actually classify this as being increasing in the argument z. Everybody got that? So that's sign-dependent monotonicity. Everybody? Okay. So that's that is the idea. Okay. Okay. So there'll be a lot of stuff on that. This is actually the basis of actually pretty much all software for convex optimization is based on something called disciplined convex programming, which means absolutely nothing more than everything you write down can be verified using that one composition rule. That's it. So in some sense, there's only one rule you need to know, which is the composition rule, and that now you're good to go. Okay. So okay. All right. We'll look at a bunch of other things, and there are some subtleties. Right. So first, remember that if I have a function of two variables, and I take the maximum over one of the variables. Before we did that before, it was the supremum over y. And the fact is, y didn't even have to be a vector. It could be anything at all. But if you take the maximum of f of xy, where f is convex in x for each y, is convex. What's cool is the same is true for a minimum, but the conditions are different and not totally straightforward. So here's what they are. It says if f of x and y is jointly convex in x and y, and then I minimize over y over a convex set, that's this thing, then this thing is convex. And some people call this, a great name for this is partial minimization. Because what it means is you have a function of two variables, they're vectors, and I minimize over one. So that's called partial. Yeah, I don't minimize over everything. It's called partial. So you would say something like this: partial minimization preserves convexity. Okay? So by the way, this would be the principle behind, for example, dynamic programming. Right? So that's what dynamic programming does. It's to minimize a big old function, like this. You start by you minimize over one variable, and then what you end up with is the value function or something like that. And this would tell you things about that being convex or not. Okay. Yeah.
Just to make sure, when you say jointly convex, it doesn't mean that it has to be convex in X separately and in Y. It can be concave in one of them.
No. So jointly convex is very strong. So if I have a function of two variables, x and y, it could be convex in x for each y, and it could be convex in y for each x. Okay? But it's not convex jointly in x, y. Okay? Someone want to give me an example of, like a simple example of that? xy. There you go. Perfect. So the function xy, they're both scalars, just literally the product. If I fix y, it's linear in x. If I fix x, it's linear in y. It's called a bilinear function, or actually, it's just a quadratic form, right? But it's definitely convex in x for each y. It's convex in y for each x, and it is definitely not convex jointly in xy. Okay? So it means weird things. It says that if you look at the function in the plane xy plane, it says as long as you're either only going vertical or horizontal, it's got the right curvature. You go this way, curves up. You go this way, curves up, which I guess you write this way, right? But you go off that grid, if you go at a 45-degree angle or something, and it does not have, the function xy certainly does not curve up. It actually curves down, right? So that makes sense? So there's a strong, so to say jointly convex is a strong condition. Okay, so here's some examples. Here's a famous one. Two vectors x and y, and I write down this is a quadratic form. In fact, what that is it's a quadratic form in x stacked on top of y, right? So that function is nothing more than x, y, transpose, and then I'll have to fill in the matrices when I see what I had over here. Let's see, what are they? Oh, A, B, B transpose C, okay? Right, so that's a quadratic form in the stacked vector xy, right? Okay, and what we're going to do is we're going to say, when is this function convex jointly?
Matrix.
What's that? Yeah, this block 2x2 matrix has to be positive semi-definite. Okay, that's the condition on which this is convex. Now let's minimize over y here. Well, how do you minimize this thing over y? I mean, we just take a gradient. You take a gradient, and here you get a term which is like 2b transpose x, and over there you get 2cy. Okay, you solve that, and you work out what it is, and you end up, when you find out what y is, you plug it back into this thing, and you get this thing. So you get x transpose. So this is, I take this function of two variables. If I minimize over y for each x, I end up, number one, with a quadratic form. So you could even say something like this. Quadratic forms are closed under partial minimization. That's a perfectly reasonable statement to make, right? But not only, it's kind of cool. If the original quadratic form was PSD, so is this one. And that's got a name. That's called the Schur complement. And you've doubtless all seen, it'd be very difficult to take classes where you don't see this, right? This is conditioning on a Gaussian random vector. This is, in electrical engineering, this is like taking a circuit and imposing conditions on some of the ports or nodes. In mechanical engineering, it comes up in every field there is, economic. I can't think of a legitimate field where the Schur complement doesn't come up. Okay, so and sometimes people call it out, sometimes they don't. I don't know. Actually, how many people have heard it called out as a Schur complement before? Okay, handful. Okay, how many people have seen it somewhere or seen something like this? Probably with some hideous notation. Okay, what field was it called out in? In the back.
In my case, numerical linear algebra.
Okay, in numerical linear algebra. Okay, good. Okay, good. All right. So and you may know that it's a basic fact of linear algebra that if a matrix is positive semi-definite, so is the Schur complement, right? Or positive definite or negative. Okay, everybody got this? Okay, so that's the minimization rule. Now we get to the perspective rule. And so this is related, if you remember, the perspective mapping takes a vector with the last entry positive and divides everything by it. And then we looked at like linear fractional mappings, and I mumbled about how that's basically the actual generic mapping you have in vision. Like if you have a camera system that looks at 3D and you look at the actual image you get on the sensor, which is 2D, it's actually got this perspective mapping in it, right? Okay, so the perspective of a function is this. It is you take a function f, and it's a function now of a new variable, which is going to be positive and a scalar. So g of x and t is t f of x over t. Right? So that's called the perspective. Here's the cool part. If a function is convex, so is its perspective. Okay? And again, that one is not totally straightforward to show, but it's true. So, and this is just not obvious. Okay? So let's look at some examples. Here's one. X transpose X is the sum of the squares of a vector, of the entries of a vector. It's convex. Okay? Well, let's figure out what you do is you just plug in wherever you see X, plug in X over T here. So you have X over T transpose X over T. So that becomes X transpose X divided by T squared. And then you multiply by T in the front, and you get this. And you go, hey, that's cool. You know what that is? That's sum xi squared over T. So it's a sum of these quadratic over linear functions, which you know to be convex. Okay? So, but you found that out without any of the pain or something like that. I mean, actually, we showed that by, I think there we resorted to Hessians, right? So, okay. Here's one. Let's take the negative logarithm. That's convex, right? Because the log is concave. So we take negative logarithm, and then let's form if we form the perspective of this, it's t, it's minus t log x over t, which you might recognize. That's the relative entropy. And then from that, it would be related to things like KL divergence and all sorts of other stuff. I mean, it doesn't matter if you haven't seen these functions before. But that just gives you a real quick way to show that these functions are convex. Everybody got this? So, okay. And let's see. So I think anyway, so it's a very, and by the way, sometimes this actually has very interesting practical interpretations of what g x over t is. And I think we'll assign some homework problems that show you where it would come up in various practical things. I mean, aside from vision or something like that. Okay. Okay. Next up is conjugate. And I understand that all of these are completely without context. So like, if you're asking like, who cares about this? Completely reasonable question to ask. Totally reasonable. But anyway, and my answer to that is you will in the next couple weeks. And also once you see these things, you will start seeing them everywhere you go, like in your other classes and things like that. So, I mean, like this is like completely central. It's absolutely central to economics. It's completely central to statistics. It just comes up all the time. It's called the conjugate function. And it looks like this. So it's this. I have a function f, does not have to be convex. Okay? And f star y, or f asterisk y, that's the pretty much universal notation for the conjugate function. It's actually this. It's really interesting. You should maximize, y is the argument here. You should maximize this y transpose x minus f of x. Okay? So that's what this is, right? And actually, this is crazy. Let's show that this is convex even when f is not. So the conjugate of a non-convex function is going to be convex. Okay? But let's see why. Any suggestions? Is it Hessian time? No. I mean, duh, right? Okay. So how do you do it? How do I show that thing is a convex function of y? Yeah.
Like the supremum of affine functions.
There you go. So here's what you do. You look at this thing, and it looks really complicated, like f is some incredibly complicated nonlinear thing. I don't even know what it is. What this says is the following. For each fix x, for each x in the domain of f, what kind of function is y transpose x minus f of x? It's affine. This is a supremum of affine functions, and it could only be convex. Okay? So, right? And so I could have really messed with you. If somebody walked up on the street and they showed f and they wrote it out in some horrible thing and it had hyperbolic cosines and sines and all that, they'd say, is this convex? You'd go like, oh my God, I don't know. But the point is, so that's that you just have to remain calm, look at it, and realize that it's like a conjugate. Okay, everybody, so that's a conjugate. And this is going to come up again. It's going to be central when we cover duality, but it also comes up a lot. And I just give you a quick example of where this would come up. Let's suppose you run a business or something like that. And X is an amount of various products that you will produce. Okay, so it's a vector of you have like n different products, and you're going to produce x1 of product 1, x2, and so on. Everybody got it? That is going to cost you f of x. Okay, so that is your production cost for producing, so many tons of this, so many units of that, and so on. Everybody got it? Okay, y we interpret as the market prices. Okay, so these are the y1 through yn are the prices for products 1 through n. Y transpose X is your gross revenue for the products you've made. Everybody got this? Okay, so this is your profit. It's your gross revenue minus the cost to actually produce those things. Everybody following this? So the conjugate then is very simple. It is the optimal profit as a function of the prices. Everybody got this? We're going to come back to this in much more detail, but maybe just planting some of these seeds in your head is not at all a bad thing right now. Okay? So that's the conjugate. And what's that? Oh, okay. Good. Everybody got it? So, other than that, it has no meaning right now. It's going to have a meaning later. Don't worry. Yeah.
Could you explain the graph?
What's that?
Could you explain the graph?
I could. Yeah. So what you do, if you want to do this graphically, here's F here. And what you do is you form XY. That's these different, that's this line here. That's this line, right? And then what you're doing is you move this line up and down until it just touches the graph. And then it turns out that point right there is the negative of the conjugate. So that's the graphical interpretation. If that helps you. I think I've decided it doesn't really help me, the graph, so it's fine. Okay? So that's the conjugate. By the way, this comes up in lots of other fields too. Statistics, probability, I go on and on and on. Let me ask, when you use the language conjugate, it conjures up certain ideas. Because conjugate is used in math in lots of cases. And mostly, here's one, complex conjugate of a complex number, right? Okay, so Hermitian conjugate of a complex matrix, right? These are conjugate. These are types of conjugates. What is an attribute you think of when someone uses the conjugate word? What's that?
It's reversible.
I missed that?
It's reversible.
It's reversible. Yeah? Yeah, okay. Let's be a little bit more specific. How do you reverse it?
If you apply the conjugate, it will return the original.
I like that. Right? So typically, when you use the word conjugate, there's sort of an implication that the conjugate of the conjugate is the original thing. Everybody got that? So the conjugate of the conjugate of a complex number is the same number back again, right? Because you switch the sign on the imaginary part and then you do it again. Okay. Do you think it's true that the conjugate of a function is the function?
No.
Why not?
Because f star is always convex, but
Yeah.
f is not necessarily.
Okay, yeah, but take it one more step. F star is convex, so F star star is convex. So if f was not convex to start with, like this function here, then there's no way F star star equals f. You're right. Okay. So actually F star star is a really cool thing. It's called the convex envelope of a function. So it's the largest convex function that fits under it. So I'll just draw that. This is advanced and I probably shouldn't be going there right now, but too late now. So here's your function. And I'll show you what F star star is. It's called the convex envelope or lots of other things. It's actually this function. It's really cool. It is the largest convex function that fits under this thing. And it's going to be this. It's going to look like that. Then it's going to go like that. And then it's going to go up like that. okay? Or here's a really cool way to say it. If you take the epigraph of the function, that's everything up here, then take the convex hull of the epigraph, that's this thing, that's the epigraph of f star star, which is the conjugate. Okay, so, sorry, this is too advanced. I didn't mean to go there, but it is kind of cool, so I don't mind mentioning it. Yes?
If f is convex, is f star star the same as f?
Yes. Awesome. Yes. So if f is convex, and there's a small technical condition, then f star star is f. Right? And that's going to be the basis of a whole lot of different things and interesting stuff. Okay. So let's look at some examples. How do you work out the conjugates? A lot of times you just have to get your hands dirty and figure out how to solve this. It's defined by this optimization problem where you maximize. And so, for example, here's the negative logarithm. Let's find the conjugate of it. Well, you have to maximize over y, which is a scalar, xy plus log x. And honestly, the way you do this, you just draw some pictures and you will find out, for example, if y is 0 or bigger, this supremum is infinity. Because, well, look, if y is 3, this is ridiculous. What happens is this thing is monotone increasing in y, and you've been asked to maximize it. So, you get plus infinity. If y is negative, it's not. And you just draw a picture and take a derivative, and you can work out what it is. I'm not going to do that, but you get something like this. So, roughly speaking, the conjugate of a log looks like a log. I mean, the sign got flipped, and there's a -1 offset, but that's that. If you have a quadratic form, 1/2 x transpose qx with a positive definite q, then it turns out that the conjugate is really cool. It's given by it's also a quadratic form given by the inverse matrix. Okay, so everybody got this? So these are just like kind of basic things. Okay, we're now going to cover two more generalizations of convexity. So first, let me give you some background, right? That there's a whole sub-industry in math of generalizing convexity. And you have pseudo-convexity and quasi-convexity, and I don't know, there's all these different types of generalizations. And, it's totally fine. It's not hurting anybody. Then usually on page 300 of the book, you'll get this horrible diagram that says if something is quasi-convex and triple pseudo-convex and blah, 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 then it's also this. And it's a big, diagram that shows you all this. Right. Okay. So what we're going to do here is we've selected the two generalizations that are actually useful. Okay. And they are quasi-convexity. That's this one. And we're going to talk about one more, which is log convexity, which is almost kind of not quite a generalization, but it is kind of. Okay, but this one is. So that's what we're going to do. So I'm just saying, if you go to Wikipedia and type in quasi-convexity, you'll find out there's pseudo-convex, and then someone showed that if it's pseudo-convex and blah 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 blah, then it has to be. Anyway, it's very complicated. So okay, here it is. A function is quasi-convex if its sublevel sets are all convex, period. Oh, another name for this is unimodal. So that's a very common name. Okay? And here's an example of a function in R. It is definitely not convex. I mean, look, there's negative curvature right there. Okay? So that's not convex. It is quasi-convex. And the way you check if it's quasi-convex is you just take your level set, like what is the sublevel set for this level? What is the set of x for which the function is smaller than this value? No, I'm down here. It's empty. See, it's the empty set. Is the empty set convex? Yeah. So that's cool. If I put something that just touches the bottom of this, I get a singleton, the minimizer. That's convex. Now, as I raise this level, you get an interval, but intervals are convex. What happens is if I raise it at the value beta, I get a half infinite interval, right? That's also convex, right? So unimodal is another name for it. And basically for a function of one variable, something is quasi-convex. If roughly speaking, it's decreasing, there's a point where it's decreasing up to that point, and then increasing above it. Okay? It's also more interesting in the vector case, right? Yeah. What's a half infinite interval? It is this. It would look like something like this. There, that's a half infinite interval. It's everything less than or equal to 3. That's an example of a half infinite interval. Actually, do people even say that? Infinite interval? I don't know. I made that up, that name. So might not be a technique, you know. But okay. Everybody got this? So that's what a quasi-convex function is, right? And by the way, it's actually super interesting. Suppose f is a function that we want to minimize, like it's an objective. What's really cool about this says then a sublevel set you can describe as all the choices that are as good as or better than, let's say, alpha. Everybody got that? Right. Like f is whatever your objective is in your problem. Let's say it's a loss function and you're fitting something, right? Then this says, show me the set of all parameters that fit my data at least as well as alpha. Everybody got that? Okay, so it kind of makes sense, right? I mean, it's an interesting, and it says that these, if you're quasi-convex, those are convex functions, okay? Convex sets, I'm sorry. Okay, so let's look at some examples. Well, okay, square root absolute value z, everybody can picture that, looks like this, right? Well, it's obviously not concave, it is not convex, but it is quasi-convex. It's also, by the way, quasi-concave, I think. Is it? No, it's not. Sorry. It's quasi-convex. Okay. Here's a weird one. The ceiling of x. That is the smallest integer bigger than your number, right? So if I draw the plot of that function, it's like a staircase, right? It just kind of like, it takes the biggest integer, whatever. The smallest integer is bigger than you. Everybody got it? Okay. Let's have a discussion right now about integer valued convex functions. Should we have a conversation about that? So let's talk about integer. Somebody tell me about integer valued convex functions. 1? Yeah. Okay. No, I like that. That was an example. That totally acceptable. There we go. Okay. So they exist. There's one. The constant function 1. Any other suggestions? 2. Okay, there we go. That's another one. Now we could go for a while with this, right? But okay, any others? Integer valued. Okay, there's -7. That's another one. No one named that yet. But okay, any others?
Set of all counting numbers.
Set of all counting numbers. Oh, let's see. I'm thinking about. I want a function that's convex and integer valued. So I'm not sure I know how to do that from. Yes. What?
The number squared.
No, it's not integer valued, right? If I have x squared, that's convex, so you get credit for that, partial credit. It's not integer valued, right? Because 1.3 squared is not an integer.
But if you do it only on the integers.
Come on. No. Stop. Okay, fine. Okay. I mean, you have a suggestion?
Step function.
A what?
Step function.
A step function. Cool. Let's try that. So a function that's, let's say, 0 for negative arguments and 1 for non-negative arguments. That's a step function? Boy, that function has so many names and so many fields. Okay. Is it convex? Oh, first of all, is it integer valued? Good. You get 5 points for that. Is it convex? No. And we were having a conversation about convex integer valued functions. Yes? The which one?
The negative Dirac delta function.
Negative Dirac delta function. Just in R, right? So, okay. I mean, that's not a function, it's a distribution, but that looks like something like this. I'm not sure what value it has here. What's that? Oh, yeah, okay. So we just make this thing, so it's going to look like this. And this is the value 1, and that's 0. Yeah. That's the function you're talking about? Okay. That's a super interesting function. That's a function of a variable, super useful. It basically is 1 if its argument is non-zero and 0 otherwise. So for example, here's a really cool thing. what's your name? What was it? Okay, so we're going to call this t of x. Okay? So what is this? This is a super interesting function. If x is a vector, what's that? What is it? That's not 1. No. It basically, what is it?
The number of zero elements.
No, it's the number of non-zero elements, right? Because I made it, maybe you can't read it from there. It's 0 if it's 0, and it's 1 otherwise. So this is actually the number of non-zero entries of x. Some people have a name for this. Some people call it the cardinality of x, the card of x, right? That comes up in a lot of things. And there's a connection to convexity we'll get to later. Okay? So super interesting, right? If x is a portfolio, if you're doing some investments, x is a portfolio, how would you say that in English? I'll tell you the correct slang in a minute, but how would you say that? X is your portfolio. Like x37 is, let's say, the dollar value you invest in some asset number 37. So what is that function of your portfolio?
Number of assets.
Yeah, it's the number of assets you invest in. Everybody got it? So, yeah. And I think they would say something like, it's like the total number of names, or I don't know what they would say, something like that. That would be close. Okay? So, okay. Now, fine, let's get back to this function. That's an integer valued function. That's awesome. It's a super interesting one and useful one because we talked about it. And now, is it convex? I'm not seeing it. No, because it's not convex, right? Because look, I could take this point and I could take this point and draw this line, and it's not below the thing there. Yeah.
There's a problem, like, if you have any discontinuity in your function, it's not convex.
Yeah. Well, that's not quite true. So, since I don't want to confuse people, but actually that's exactly what I'm probably about to do. But so the theory of here's a theory of convex integer valued functions. They're constant. Okay, that's like the answer is their functions 1, 2, minus 13. Okay, that's not totally true, and there's some weird sick. But this is sick, and you shouldn't even hang out with people who make up examples like this. But so, here's one. Here's a function. It's defined on minus 3 to plus 2, and it takes the value 7 inside the interval, but then at minus 3 it takes the value 10, and at 2 it takes the value 12. Okay? So that's an integer valued function, no doubt about it. It only has the values 7, 10, and 12. And it's convex. Okay, everybody got that? You don't think it's convex? Ooh, I like that. Ooh, yeah. Okay, that's fine. All right, we can do that. Let's do chords. So for chords, I take 2 points in the domain, right? And I take the chord, right? So if I take a point here and I take a point here, and I take the chord, that's the line between it, does it lie above the graph? It lies on the graph, so it's cool, okay? What if I take this point and some point over here? Now, the chord looks like that. Does it lie above the graph? Okay, and finally, what if I take that point and something in here? I get a chord that looks like that. It lies above the graph. And then finally, what if I take these two and I draw the chord like that? Does it lie above the graph? The answer is yes. So, cool. Okay, so it is convex. This is sick and weird, and you shouldn't hang out with people that make up examples like this. Yes?
Wait, so should I amend the statement to, like, if it has any discontinuities in the interior, then it's...
That's correct. There's your amended statement. That's good. But okay, so if you didn't follow this, then don't worry, because you're probably better off if you didn't actually. So that's fine. Okay, so then you get some pretty weird stuff. I won't go into some of these, but we'll do one example. This is like quite practical. It's the internal rate of return, right? So this is from, I don't know if you could, like accounting or something. Okay, so here it is. So I have a cash flow, and it's given by a vector, which is n plus 1 long. And the entries are labeled like x1, x0 up to xn, right? So that's a cash flow over n plus 1 periods, right? I mean, it depends. X0 might be like right now, right? So for example, if you bought a bond, let's just say, if you bought a bond, x0 might be negative. It's how much you pay for the bond. Then x1 might be the coupon payment you get for that bond. X2 is the coupon payment in period 2. And then xn might be the maturity, and you get both back the coupon payment and the face value. By the way, you don't have to know what a bond is. I'm just like, you don't need to know this. But it's not bad. It's just cultural, I don't know, enrichment or something. Okay? Everybody got that? Right? I mean, this could be an investment made by a VC firm in a startup, right? So they wire transfer, $12 million into a bank account, right? That's X0. Then X1 is probably 0 for a startup. X2 is 0. And then maybe sometime later, somebody acquires them, and then one of the X's is really big. Everybody got this? Okay, so that's a cash flow. Okay, and we're going to assume, this is just to make it simple, to make the definition simple, that's fine. We're going to assume that x0 is less than 0. That means that the first point in that, the first cash flow is something we pay, we invest in, right? Because it's a negative cash flow to us, it means we're investing, x0, right? Then we're also going to assume, we don't assume that the signs of x1 through xn are positive. We may pay more in. They can come back to us and say, sorry, we need a bridge loan. Or whatever, or we don't, that's it. Or we can't meet payroll, so we need more money. That's fine. But we will assume that simply the sum of all the things is positive. And what that means, and this is just to make it simple. It works in other cases too. What that means is that the total of all the cash payments it was not at least a disaster. That's what it means. It means, right, so that's what it says. Okay. So people talk about the present value of the cash flow. And that's going to be, with an interest rate R, it says you simply multiply. So what you do is you say that a payment to me at time I, at period I, is going to be worth 1 plus R to the minus I. So if R is 5%, and it's 10 years, it means that it's worth to me, only, 1 over 1.05 to the 10. Right? I don't know what that is, like 1.8. Well, 1 over 1.8. Let's say it's 0.4. I have no idea what it is. 0.5. I'm making that up, right? So these are the discounted cash flows, and this is called the net present value, right? So, and these are just completely standard concepts in basic accounting. Okay, everybody. Okay, that's the present value, and it's a function of the vector x and the interest rate r. Okay, and now I can tell you what the internal rate of return. It's called the IRR. It's the smallest interest rate for which the net present value is 0, right? And I think the argument about it, if you're teaching MBAs or something, is the idea is you would be ambivalent if I walk up to you and I say, hey, I got a great deal for you, invest in this thing, right? And then we work out the internal rate of return, and it turns out you could get something else. You could get a bank account or something like that with the same interest rate. Then you'd say, why should I invest in your stupid thing? I'm going to take it to the bank or something like that. That's the idea. Okay? Everybody got this? So, and this is, by the way, this is not part of the class. You don't need to know this, but it doesn't hurt to know it. This is not bad. Okay. All right. So it turns out the internal rate of return, which is actually complicated, right? Because you actually, this thing here is a polynomial in 1 over 1 plus r. Yeah, it is a polynomial. So this actually requires solving a polynomial equation. So, hello, if there's more than 5 periods, then there's not an analytical formula for it, but who cares, right? Everybody following, right? So it's complicated, right? So this is the internal rate of return. And it turns out it's quasi-concave, which is just like weird. I doubt anyone in accounting would know this. In fact, I'm virtually certain of that fact. I have friends in accounting. So, and I'm not insulting them. I'm just saying it's not how they think. So it's fine. It's quasi-concave. So what does it mean to show something's quasi-concave? What you need to do is you need to show that the super level sets, right? For quasi-convex means the sub-level sets are convex. Quasi-concave means the super level sets are convex, right? And so let's look at that. So let's look at the set of all cash flows here that satisfy the internal rate of return is bigger than, let's say, 5%. That's what we're going to look at, right? So what is that? If your internal rate of return is bigger than or equal to 5%, it means that between an interest rate of 0 and 5%, your net present value was still positive, right? Because this says that your net present value with an interest rate of 0 is positive. That's what it says. It says that there's no interest, it's low interest time. So just add up the numbers, and that says it's positive. So the project looks good if the current interest rates are 0, right? As you increase it, what you can figure out is actually this thing decreases, and of course at some point it goes through 0. When it goes through 0, that's the internal rate of return. Okay? Okay, so what is this as a function of x? What is that? So, oh, that's a linear function, right? But then this says the linear function is bigger than 0. So what is that? It's a half space. It's an open half space, you would say, because it doesn't have the bigger than or equal to, but it doesn't matter. So it's an open half space, right? Oh, and an open half space is convex, okay? And for the IRR to be bigger than R, this thing has to hold. You have to be in a family, in an intersection of a set of open half spaces. That's convex. Everybody follow this? So, yes?
Does it matter that like you're doing an uncountably infinite intersection?
No, that's the cool thing. Yeah, it's a great question. Max and min, right? They generalize to sup and inf. And in fact, they can be over infinite sets. And we saw a whole bunch of examples, right? Where that's the case. This is another one. So yeah, so that's a very good thing to remember. It's like these rules about max and min, they depend, they can be on infinite sets, right? So, okay, everybody got this? Yeah.
So when we talk about concavity, not convexity for this one, the super level implies concavity, but the intersection of open half spaces are also concave.
No. No. So open half spaces are convex. Be careful. There's no such thing as a concave set, or at least I don't know what it is. I don't think it makes any sense. So we don't have concave. It's weird, right? There should be something. But I don't know what a concave set is, right? Oh, you have concave mirrors and concave lenses, but I don't know why we don't have concave sets. Anyway, we don't. So here what you want to show this quasi-concave, you want to show that the super level sets are convex. Right. So, yeah.
I got the part which the summation of 1 plus r, that's a open half space, but where's the intersection coming from within that?
Because here's what has to happen. For x to be a cash flow with an internal rate of return exceeding r, then this inequality has to hold for all real numbers between 0 and capital R, right? And so basically you're in the intersection of all of those half spaces. For any fixed number R, you get a half space. But you got to satisfy that for all numbers between 0 and R, and that's an intersection. Did that make sense? Cool. Okay. So I'll just say a few more things, and then we'll continue next time. So for quasi-convex functions, you have a modified Jensen inequality. It's actually quite interesting. Jensen's inequality says that f of a mixture is less than the mixture of f's. That's Jensen's inequality for a convex function. For quasi-convex, this gets replaced with the max. And the picture is, I don't have a picture there. I should. I don't know why I don't. Okay, so here's what it looks like. Here's a quasi-convex function, right? And then here's like x, and here is, here's x and here's y. Convexity says that if I draw a straight line between here and here, the graph lies below it. But that's clearly false for this example. And sorry to pick a color which is unreadable. Sorry about that. So, okay. So this thing says for quasi-convexity, here's what you want to do. You take the max of the two. And so it basically says the graph has to lie under that thing. And it does. So it's cool. So that's quasi-convex. Okay, so we'll quit today. I have to say we are very close. We're about 10 to 15 minutes of lecture through this long slog of all the math. So, but the sun will come out, I would say about 20 minutes into next Tuesday's lecture.